Isotopes, nuclei with the same number of protons, are the same element. But when they have different numbers of neutrons, they're called isotopes. Isotopes of an element have the same number of protons, Z, but different numbers of neutrons, N, and therefore different atomic numbers, A. For many elements, there are a few different isotopes that occur naturally. Isotopes of a single element have the same chemical properties, but they can have very different nuclear properties. Natural abundance is a term that describes the percentage of an element that occurs as a certain isotope in nature. Isotopes that don't occur in nature can often be produced with nuclear reactions in the laboratory. So far we've discussed the atomic mass number, but that number does not really specify the mass of the nucleus. Atomic masses are specified in atomic mass units, or U. These are defined by specifying that a neutral carbon atom with 6 protons and 6 neutrons has a mass of 12 U. The U can be found to be 1.6605 times 10 to the negative 27 kilograms. Not necessarily a useful unit. And just like we introduced the electron volt when dealing with atomic energy levels, we're going to bring in the MeV, the million electron volt, to work with nuclear energy levels. Consequently, we're going to use Einstein's mass energy equivalence relation, E equals mc squared, to convert the U from kilograms to MeV per c squared. The calculation is shown below, and the result is that one atomic mass unit is equal to 931.5 MeV per c squared. The table below shows the rest masses, that is, the masses of objects that are not moving, for various parts of the hydrogen atom and for the hydrogen atom. When you look at this table, you can see that the masses in kilograms are rather unwieldy, a lot of decimals, and scientific notation. When we use the atomic mass units, we can see that we're looking at relatively small changes that appear well past the decimal point. The MeV per c squared is more convenient, and it's easier to differentiate the masses of the various objects. Because the atomic mass unit was defined for carbon-12, it is the only isotope where the atomic mass in U is exactly equal to the number of protons plus neutrons, the atomic mass number. For other elements, their exact measured atomic mass is always slightly different from the number of protons plus neutrons. Many periodic tables list the atomic mass in addition to the chemical symbol, the atomic number, and the mass number. This atomic mass is a weighted average of the masses of the isotopes of each element. For example, carbon has 15 known isotopes with neutron numbers that range from 2 to 16. 2 of these are stable isotopes, and together they make up nearly 99.99% of the carbon on Earth. Other isotopes are also present, but in trace amounts. So we have carbon-12 with 98.93% relative abundance and carbon-13 with 1.07% relative abundance. If we want to calculate the atomic mass, we're going to take the weighted average of these. So we take 0.9883 times 12 and 0.0107 times 13. The result is that the atomic mass listed on the periodic table will be 12.01.